I'm Eden. I have good news. When we're done, there's a break.
That's right.
And if you're interested in any of the stuff we're talking about, there is a SNIA SSSI table, and they've got the hardware and the workloads and the data that you're going to see here, so you can ask about it there. My name's Eden Kim. I'm with Calypso. I'm going to co-present this with John Kim of Mellanox. And I don't know if we're related.
We might be. We're probably distant cousins.
OK, so how does this work? OK, so today we're going to talk about four things. We're going to talk about performance, benchmarking comparison in terms of test workloads and the test plan. Then I'm going to talk about direct attached storage and the test results. And then John's going to talk about fabric and remote testing. And then we're going to have a conclusion and question. OK? You can download the PowerPoint or the PDF. There's a lot of detail in there that we don't have time to go over here. So we'll give you short answers. And if you want more detail, you can either look at the PowerPoint or talk to us outside. OK, so test plan. Pretty simple. We're going to find a real-world workload and define a workload from it. Second, we're then going to test the sample pool as direct attached storage. And then third, we're going to test it over remote or fabric. Last year, we did a presentation here using a real-world workload, which was a 24-hour retail outlet SQL Server workload. And this year, we're going to do a GPS nav workload, so it's a little bit different. And in addition, last year, we looked at memmap, msync, and non-temporal writes. This year, we're going to look at block I/O performance and look at it in a comparison between direct and fabric. It's off. It's on. OK, for the sample pool, there's three storage devices. One is a NVDIMM-N, 16 gigabyte. The second and third one are both U.2 NVMe devices. One's a 3200 gigabyte 2019 model, and the other one is a 2000 gigabyte 2018 model. So U.2-H is this year's drive, and U.2-I is last year's. The test platforms are basically all pretty fast DDR4 motherboards with different types of OSs. The interconnect is over a Mellanox high-speed NIC. The NVMe over Fabric Rocky is 100 gigabits per second, and John will talk about that more in detail when he goes up here. As far as the source of the real-world workloads, we're going to use a real-world workload that on the SSSI website. It's not the SSSI website, but it's a website where the SSSI posts reference workloads that you can download and look at. It's at testmyworkload.com. So last year's workload is up there, and this year's workload is also there. OK, so this is the 2018 workload. What you're looking at here is timeline along the x-axis, and the colored bars are I/O streams. And the basic takeaway from this slide is it's a 24-hour coarse grain capture where every data point is an average over 5 minutes. There's a lot of different activities going on. It's a very heterogeneous workload, so you get a lot of different performance peaks and valleys. And the queue depth is pretty high. When you look at this year's, it's going to be a much more homogeneous workload. It's only 30 minutes, but the steps are 1 second. And you're looking at a much more finer grain, a higher IOPS activity. So what we do is you take the workload and you select from the workload a number of I/O streams that you want to constitute the real-world workload that you use to test with. If you go to testmyworkload.com, you can look at this guy. It's workload demo number 7. And that's what we call an I/O stream map. And basically, it shows you all of the I/O streams that occur from the beginning of the capture to the end of the capture. So again, it's a 30-minute capture, and each data point is 1 second. So there's 1,800 data points. The thing to note that is, from a process point of view, the I/O streams are tagged with process IDs often, and you can filter or parse to those that you're interested in. So in this case, we're interested in the MySQL and the SQL Server, and it's blown up there. You can see it's 68.9 and 12.4% of the total IOs. So when we make the workload, those are only the IOs we're going to take. The second thing is you'll notice that there's total IOs occurring over the 30 minutes. There's 176 different IO streams. Okay, an IO stream is a distinct transfer size, read-write mix, and block size. Well, we're only going to take 9 of those, but the 9 that we selected constitute almost 90%, 89% of the total IOs. So what we've done is you've taken a 30-minute workload, we filtered it down to the SQL Server process IDs, and then we also filtered it down to the main 9 IO streams that are 89% of the workload. And so this workload will be used in several kinds of tests, and we'll see that in the next slide. There's 5 tests we're going to run. There's 1 synthetic workload test, and there's 4 real-world workload tests. The synthetic test is a random 8K 6535 read-write mix, which is kind of a standard industry-used SQL Server emulation. Then we're going to use 4 real-world workloads. 2 of them are dynamic and 2 are fixed. So with the SQL DIRTH workload, what you're doing is you're taking that random 8K 6535 read-write mix, and you're running it to steady state, and then you change the queue depth and thread count over a range of thread 32, Q32 down to thread 1, Q1. So you're varying the band intensity, and then you can plot the performance at different points of total outstanding IOs. You do the same test again with the real-world workload. So for the real-world workload, the percentage IO streams that you have are applied for every step of the test. So if I have 25% random 4K writes and 75% random 4K reads, for example, every step of the test would be that same 75-25 mix. When you go to the replay workloads, these are more dynamic. They're fixed. They're not fixed. They're changing with every IO step. So instead of having all steps being the same, you're replaying the IO combinations that you saw during the capture. So when you look at a capture, you're going to notice that there's many IO streams that are occurring from time to time in different combinations and at different queue depths. This dynamic changing workload has a big impact on performance. So when we do a replay test, it's going to have a much different effect than applying a fixed and constant workload. After we do the replay test, then we take those 9 IO streams that are in that real-world workload, and we just do a traditional steady-state test for each individual IO stream, so you can see how the drive performs to those specific IO streams. So if a random 4K write is part of the 9 IO streams, you'll be able to look at that independently and then compare it to your benchmarks of what your manufacturer spec might have. Am I going too fast? I can slow down. We're ahead of the curve. Okay, so this is what the synthetic DIRTH test looks like. A DIRTH test, DIRTH stands for Demand Intensity Response Time Histogram. And this is the test where you take the workload, you run it to steady state, and then you change the thread count and queue depth over a loop so you can see where the optimum performance is in terms of IO and response times. In this case, you have 2 IO streams, random 8K read and a random 8K write, and a 65-35 read-write mix. If you look at the real-world workload, this one has 9 IO streams, and they're listed here on the left. They go from 16K write, 4K write, half K, so on and so forth. And that percentage mix of those 9 IO streams is applied for every step of the test. So just like the 65-35 read-write mix for the random 8K, you're going to run this one to steady state with all 9 IO streams. And then when you get to steady state, you're going to change the queue depth and thread count and find out its optimal point. So these 2 tests, the DIRTH test for the synthetic workload and the DIRTH test for the real-world workload, are run exactly the same in terms of steps, but one has 2 IO streams and one has 9. After you run the fixed workloads, what we're really interested in doing is to replay the test. So the replay test replays the combination and sequences of IO streams that were in the capture. So if you had 1 IO stream, then 9, then 8, then 7, then 6, then 9, or whatever it is, you're going to replay that capture to the drive in the proportion and the percentages that were in the capture. Okay, so here's that IO stream map of the 30-minute workload, and we've just captured a few workload spots every 5 seconds, so you can see that there's different IO streams for each one in different percentages. So for this replay test for 30 minutes at 1-second intervals, you're going to have 1,800 test steps, and each test step will be comprised of a different number of IO streams and different queue depths. Okay, so if you didn't understand all of that, you can go out to the table and we'll just show you. Okay, so in this section, we're going to look at some data. And basically, the data we're going to look at the synthetic random AK6535 rewrite mix, your synthetic lab test. Then we're going to compare that against the real-world workload as a fixed test. I'm good. And then we're going to look at the replay tests. And at the end, we're going to break it out into its individual streams and see how each stream performed. Okay, they're all going to look like this chart. So basically, what you have in the upper left-hand corner and the middle, those are the two workloads. Okay, the synthetic SQL workload is 6535 random AK rewrite, and it's the yellow bar. The green bar is the real-world workload, 9 I/O streams. So the first column is the NVDIMM-N, 16 gigabyte. The middle column is the U.2 3200 gigabyte, and the right-hand side is the M.2 U.2 2000 gigabyte. So basically what you're seeing here, the synthetic lab workload has a higher performance than its real-world workload counterpart. There's a lot of reasons why we'll go into later, but you can see clearly that the real-world workload is not giving you as many IOPS as your synthetic lab workload, because in the lab, you're fully saturating the drive, whereas when you take a real-world workload, it has a lower demand intensity and different I/O stream content. Here we're looking at the synthetic DIRTH workload, and we look at the IOPS, which are the yellow box, and the average response time, and the 5 nines response time quality of service. So we use QoS to represent 99.999% response time. So you can see that for the NVDIMM-N, it has 1 million IOPS. For the first U.2, it has 213,000, and for the third U.2, it has 72,000. This is kind of expected. When you look at the response times, the average response time for the NVDIMM is 15 microseconds. For the first U.2, it's 300 microseconds, and for the last U.2, it's 890 microseconds. And for the 5 nines, you're looking at 90, and then 11 milliseconds, and then 25 milliseconds. Okay, so there's an order of magnitude difference in the response times between NVDIMM and U.2. Looking at the same test, but now looking at the real-world workload, okay, the previous one was the synthetic random AK6535. This one is looking at the 9 I/O streams, the same test. Again, the IOPS were lower, but the ordinal ranking was similar. It's 715,000 for the NVDIMM. The U.2 was 136,000, and the second U.2 was 20,000. Looking at the response times, you can see for average response time, you have 11 microseconds, 230 microseconds, and you go up to 1.5 milliseconds. So you have the same relative performance, but the absolute performance of the IOPS is lower when you look at the real-world workload. And this is largely due to 2 or 3 things. One, you have a different combination of I/O streams that has an effect on performance. Second, as we look at it later, you'll notice that the real-world workload is predominantly writes, where the synthetic workload had 65% reads. And the third thing is when you do an I/O capture of a real-world workload, it has a lower demand intensity, so you're not saturating the drive. So because you're not saturating the drive using a real-world workload, you can't really tell how the drive will be. So what we do is when we do the replay test, we have a replay scaled test, where we scale up the Q depth by a factor of 2, 4, 8, 16, or 32, so that we can see if the drive is fully saturated with a real-world workload replay, how high will the IOPS be and what will the response times be. So here's a replay test. So here you have the green bar, which was the fixed 9 I/O streams. Remember that 713,000 number? So when we switch and we just replay it in the sequence that the I/Os occurred, it drops down to 380,000, half as much. But again, the demand intensity is low. So if you multiply the Q depth for each step by 32, you go from 380 to 822,000, which is higher than the synthetic workload. Same thing for the U.2s. I went from 136 down to 129. But then when I scaled it up, I got back up over the original value. And for the third one, we didn't quite get there. When you look at the scaling, you can look at, this is for the one drive, the NVDIMM-N. And the first column is the native Q depth, and then we multiply times 2, 4, 8, 16, and 32. You can see the curve where the IOPS start to spike up at a scaling of 32, and you can see that the response times are pretty linear. So this tells us that the NVDIMM-N has probably not been saturated, and if we were to double the queue depth factoring again, you probably would have another increase in IOPS and perhaps a continued linear response time increase. When you look at the U.2 drives, they do get saturated. So you can see from the IOPS, you have a peak there at queue depth 4, where it gets to 155, and then when you go to 8, it actually goes down, and the response times start to go up dramatically. So we think that this U.2 gets saturated at a queue depth scaling of 4 at 155,000 IOPS. When you look at the second U.2 drive, it has the same profile. Here it peaks at 9,000, then it goes down to 8, and even though the IOPS continue to go up, the response times are going up much faster. And so response time being the figure of merit for this type of test, you probably want to stop before the response times get outside of what your application can handle. I mean, if you have an application that doesn't care about response times, go ahead and go for the 13,000. But if you have something that has a lot of transactions, you're probably going to want to stay down the left side. And then this is the individual streams. So remember, that real-world workload had 9 I/O streams, and we either tested every step, all 9, or we did a replay where those 9 I/O stream combinations changed. So we took each of those 9 I/O streams, and then we just took them and independently ran them each to steady state. So in the case here, the left-hand side is a sequential 4K write, and it's 1.2 million IOPS. If you jump over to the middle, sequential half K writes is 2 million, and so on and so forth. So you can see that individually, running to steady state, fully saturating the drive, you're getting million, million and a half, 2 million IOPS, whereas in the previous test, you were at 700,000 and 1.2 million. So this is a case, again, showing that lab synthetic workloads are designed to saturate the drive and get you the maximum performance that you can get. When you use a real-world workload, you're rarely going to saturate the drive, and so you have to determine how much a range of demand intensity you expect to have or how much you want to test. This is the U.2, and you're looking at both the U.2H and I. So it's the same I/O streams. One drive is the yellow bar, one drive is the green bar. So you can see again that the individual I/O stream performance is all over the map. I mean, if we were to look at sequential half K writes, 417 versus 1700, well, which drive should you get? Well, I want to get the one with 400,000, sequential half K writes. But that has very little to do with the total real-world workload. So you have to be careful looking at synthetic benchmarks because they do not reflect the actual workload that your device is going to be in. And furthermore, you can't evaluate how well your drive is actually going to work unless you know what the real workload is. Ding. John Kim from Mellanox is going to improve the presentation.
All right, thank you. Thank you, Eden. All right, so so far what we've seen seems to make sense. I don't think it's too surprising. We've seen that the persistent memory in the case of the NVDIMM gives you better performance than the U.2s. The newer U.2 is better performance than the older U.2 NVMe SSD. And we've also seen that real-world workloads give you different results than the synthetic workloads, and it's not always in the way you expect. So it's good to look at the real-world workloads. And this has all been with direct attach or local, either persistent memory or an NVMe SSD. So now let's look at it over a fabric. So fabric, of course, enables remote access. And so earlier, Andy and Neil and some of the other people spoke about the ability to do it both. You have local and you have fabric, and they're different usage models. So what we did is, in this case, we hooked up 2 servers connected with 100 gigabit Ethernet, in this case using RoCE or RDMA over Ethernet, but you can do fabrics with other connections. You can use also Fiber Channel, InfiniBand, TCP/IP, or also Intel and Cray have other interconnects that you could use for fabrics as well. So in this case, what we did is we took this either persistent memory or NVMe SSD, and we mapped them as block devices and over the network. In this case, using the NVMe over Fabrics driver. There are other ways to do it. So they're actually being treated as block storage, but with a Fabrics driver. But again, there are other ways you could treat it, but that was the simplest way to get this set up running and test it. And we compared the Fabric performance to local performance, as well as the performance of the persistent memory to the SSDs. One thing to know that's important is, of course, Fabric always is going to add some latency. But this latency may or may not be noticeable, or the degree of effect of that extra latency on the fabric will depend quite a bit on the workload. So in some workloads, or if the media is slower, like say the slower SSD, you may not notice that extra fabric latency. And also we'll see that in some workloads, the fabric latency is more noticeable than others. So in the first test here, this is a synthetic workload, and we're comparing the direct or local persistent memory versus the remote persistent memory. And we see that, of course, interestingly, the IOPS is lower with remote, but it's only slightly lower. And we see the response times are significantly higher, not hugely, but the response times or latencies, looking at average and the 5 nines QoS, or long tail response times, which can be really important for a lot of applications. We've seen customers often say that the long tail latency is much more important than the average latency when you're looking at critical applications. So we see that it is higher. It looks like for the average latency is 4 times higher going over the fabric. Again, this is to the persistent memory NVDIMM. And then the long tail latency, however, is just slightly more than twice instead of being 4 times. And this is the latency is on a logarithmic scale here. So again, the long tail latency is only about twice as high, even though the average latency is 4 times. And it's kind of interesting that the total IOPS is very similar, but this is a synthetic workload, again, comparing local to over the fabric. So now we apply the real-world workload, the same workload that Eden talked about earlier, where it's built from this GPS navigation portal, and it's composed of 9 different I/O streams. And again, we see that and again, this was a bit surprising to me, that the remote IOPS is higher than the local IOPS. Normally, you would expect the opposite. And so we can discuss that more later, but the latency was still higher for over the fabric. Again, not surprising, because the fabric is, of course, adding physical latency. But what I thought was interesting in the real-world workload, it seems that the difference in the long-tail latency is actually bigger, but the number of IOPS was higher for the remote than versus local. So before, we see that the long-tail latency in this case for local is now about 9 times higher than the average latency. Before it was about 7 times, about 6 times higher. Now it's 9 times higher, long tail versus average. And then on the fabric side, it is about 5 times higher. And previously it was about 3.5 times higher. So the real-world workload, you can tell, is causing differences in the latency aspects when you compare both remote to local, persistent memory versus local, as well as comparing the 5 nines QoS latency to the average latency. So definitely big differences when you go from a synthetic workload that's steady state, just 1 I/O stream, to this real-world 9 I/O stream workload. And then if you split up into those 9 different I/O streams and analyze, we see that for most of the data, the local has a higher IOPS. Local's in yellow versus green is the fabric. But for a few of the streams, let's see, for the small streams, we see that for the bigger streams, we see that the fabric IOPS is actually higher for the larger streams, and the local IOPS are higher for the smaller the streams with the smaller I/O sizes. Keep in mind, this is 9 different I/O streams, all different kinds of write, mixture of sequential and random write. So you would expect that normally you would expect all the streams to have higher IOPS with local versus fabric. We see that, and that's true most of the time, but not for every stream. And then if we look at response time instead of IOPS, again here, lower is better. Yellow is local, green is remote. We see that most of the time, again, for some of the workloads, the response time is higher on the fabric, what you would expect. But for a few of the workloads, I think, again, the larger ones, the response time can actually be lower. The average response time, not the 5 nines, can actually be lower on the fabrics for some of those workloads, typically, again, the bigger ones. Okay, so now let's look at those U.2 NVMe SSDs. So we looked at persistent memory. Let's see if the same thing applies when we're comparing local to fabrics for the same SSDs that Eden tested in a strictly local sense, or a strictly local benchmark. So this is looking at the high level, or the faster, newer U.2 NVMe SSD. And again, on the left is local, or direct attach. On the right is the remote fabric. It's not remote persistent memory, but it's remote NVMe SSD, or NVMe over fabrics. So again, not surprisingly, well, surprisingly, the Fabric's workload has higher IOPS, and we can talk more about why that might be later, though we didn't have time to dive into the details of maybe what happened there. And again, but not surprisingly, the latency is higher on the Fabric side, both the average latency, which is about 50% higher, because again, it's a logarithmic here, so it looks a little higher. It's really almost 50% higher. And then the 5 nines QoS latency, or QoS response time, is just slightly higher. So that's interesting. Again, synthetic workload. Same thing now with the older, slower SSD, same results. Remote IOPS is, interestingly, higher, but latency is also, of course, higher for remote. We said that latency is triple for the average latency, and it's almost double. It's actually basically double for the long tail latency. Again, remote versus local. Now let's look at a real-world I/O stream. So again, we both believe that this real-world I/O streams are a better test of storage or Fabric's performance than the synthetic workloads, which honestly is what traditionally we run in our labs because we didn't previously have access to the kinds of testing tools that Calypso has that can replay these real-world workloads that are a mix of different I/O streams. So that was a very interesting part of the testing from the Mellanox side, something that we traditionally have not been able to do. We do synthetic workloads all the time. So again, this is a real-world workload, and this is the faster NVMe SSD, the faster, newer one, comparing local to NVMe over Fabrics. So the IOPS are lower in the case of real-world. So with synthetic, remember, we said, wow, Fabrics is faster than local for synthetic. But with real-world, Fabrics is lower, has a lower IOPS level. And again, just like with the synthetic, it has a higher latency period. But the difference in latency on the real-world workload is not as great. It's smaller than the difference in latency on the synthetic workload. So previously, we were seeing latency that was from 50% higher, usually, to 100%, to almost double. Here we see that the latency, while higher for the real-world workload, average latency is just slightly higher. It's like 10% higher or 8% higher. And the long-tail latency is also only about 20% higher, instead of previously being like 50 or 100% higher. So again, we see a big difference going from a synthetic workload to a real-world workload. And this is just one of many real-world workloads that are available on testmyworkload.com or that you can replay with this Calypso CTS software. Again, Eden talked about this one happens to be 9 different I/O streams that are mostly write, a mixture of random and sequential writes. So the results could be different if we used a workload that had a mix of reads and writes, a real-world workload. And the synthetic workload was like a 65% read, 35% write. So again, we're seeing interesting differences between a synthetic workload and a real-world workload when comparing local to Fabric, both for the persistent memory and for the SSD. And again, similar results. This is, again, the low-speed or lower-performing older SSD. One difference is that while the performance is lower, the difference in IOPS, Fabric's is lower IOPS than local. Again, what you'd normally expect. But the difference is very, very small in IOPS. It could be that we were just limited by the SSD, and that's why that difference is so small. And again, the latency, while higher on the Fabric side, and this is real-world workload applied to the older SSD, the difference is actually pretty small. You're seeing a latency difference of maybe less than 5% for average, and again, probably a little bit less than around 10%, 8%, 10% higher for the Fabric compared to local when you look at the long tail or QoS latency. Okay, actually, did I get that mixed up? So here are the good point. All right, so interesting. But I would say they're so close, we could almost call them even. But it's actually the long tail, right, the local had higher latency by a tiny bit compared to the Fabric. So I think we should, in this case, say it's about even when you have the slower SSD, where with the faster SSD, and definitely with the NVDIMM, you're seeing some significant differences. Okay, where again the local has significantly lower latency than the Fabric. So it appears, while we don't have enough information to draw a firm conclusion, that if the storage media is limiting things or is the gating factor, then the Fabric going to Fabric doesn't make as much of a difference. Okay, now I've lost where I was. So we were real-world workload.
You are here.
Okay, so I think I'm ready to go to the next slide. Now, real-world workload. Comparing the two different, sorry, this is again on the slower DIMM. I did this one. All right, now let's split out, again, real-world workload, break it up by different streams. How do the different streams compare or fare when you do local versus remote. Again, with the high-end or newer, faster NVMe SSD, we see that most of the time, as expected, the yellow or local IOPS are higher than the remote. But the difference is not very big. And we see that for just three of the workloads, the IOPS are slightly better or significantly better for 4K. So there might have been something in that fabric that was optimized for 4K I/O on the fabric side for 4K writes. And in one workload, it's actually basically about the same. For 16K random writes, they really have the same IOPS. So real-world workloads split out by stream. You have similar performance, but generally for smaller stuff, the local is better for IOPS. Average response time, here again, lower is better, where previously lower was higher is better. And we see, again, for most of the workloads, local is better. Interesting enough, in this test, it's a mix. So for some, the yellow bar or local has lower, better latency, and the fabric has a higher latency. But again, for generally the bigger write blocks or bigger write block sizes, the fabric actually has slightly lower average response time than local. But again, it's pretty close. Now if we look at, the U.2 NVMe SSD, the older one, then we see that things are pretty similar. Generally for IOPS, local is better, but it's usually close. And the average response time, we see that, interestingly enough, the fabric solution, and this is with the newer SSD, that the fabric solution is often better, but again, it's very close depending on the workload. So, get to the conclusions. Eden, why don't you come back up?
So we'll split them. I'll do the first four. So clearly, persistent memory is faster than U.2. It has faster IOPS and lower response times by orders of magnitude, or an order of magnitude. And we saw that the synthetic workload was faster and more IOPS than the real world. But what jumps out is a 65% read, and the real world workload was 100% writes. So there's a difference there. For the replay test, the lower demand intensity and the dominance of writes generally made it a lower workload performance. But when we scaled it up, we saw it equal to, if not greater than, the fixed workload. For fabric?
Okay. So with fabric, obviously, we could see that the fabric is always going to add some sort of latency to the connection. But depending on the workload and the performance of the media, again, in this case, whether it's an NVDIMM, which is faster, or a faster SSD or a slower SSD, you may or may not actually see that difference in your benchmark results. And that the synthetic benchmark results tend to show a different set of results when you compare local versus fabric than a synthetic workload. So there were talks earlier that while fabric is lower, there may be cases where disaggregating the storage or having access to a slower cache that's larger, which gives you a much higher set of cache hit rates, or being able to put a bigger workload in memory, a slower memory, may still be better than having a small amount of faster local storage or regular DRAM or persistent memory, which you can't use as extensively or leads to more cache misses. So I think it definitely shows that while you have to factor in the extra latency of the fabric, and that latency should theoretically have a bigger impact as the media gets faster and faster. So as you go to persistent memory, fabric latency should be much more of an issue than if you have flash-based SSDs. That on some workloads, the difference is pretty small. And in a few edge case workloads, fabrics can sometimes run faster than local.
So I would make 2 points. Calypso has a lot of testing, more than we want to admit. And I would say 2 things. Number one, for the fabric, we expect there to be an overhead on response times. But compared to the published specs, we see real-world differences much lower. So in other words, the fabric is not as taxing in the real world than the specs. So the specs say, oh, you might get 20% addition. We're seeing 10%, 5%. So that's a good thing. The second thing is people always ask me about performance. Why? I never go to why because I don't know why. All we know is what. But one thing I do know is whenever you get a question about performance, there's 2 things you can say. One, it depends. And in this case, it depends on the workload, the demand intensity, the storage type, the interconnect. And the last thing is, it's always about the workload. Okay, so that's what we have. questions?
But my one comment is that, again, as I mentioned previously, we have lots of experience running synthetic storage workloads. It was pretty exciting for us to be able to run the Calypso CTS software because it was perhaps one of the first chances, not only chance, but first chance for us to be able to go out and pick different types of real-world workloads and play them against the different types of storage. So first chance for me. I think we have other people who did like Spark and Oracle workloads and stuff. So I thought it was very useful for testing performance. Questions? Okay.
I'm curious why you didn't test Optane SSDs.
We tested a lot of things, but we only had 40 minutes, 20 minutes each. So as I said earlier, we didn't touch any of the memory map engine, MSync. We had SSDs in here before. We had other things in here before that were taken out for a variety of reasons. So in the allotted time, this is what we have. But we do have data on other things if you want to.
Yeah, like for example, we only tested block access. We didn't get to test file access or direct memory map. Those could also be interesting, but another event, another talk.
But if you look at last year's presentation, we did do that. So it's on the website.
Good, yeah.
Be-
Tom.
Be nice, Tom.
Tom. Let me hide
Oh,
behind
this
you.
is for John.
That's right.
Yeah, well, it's pointed a little at John. Tom Talby, Microsoft. John, you sounded a little surprised that the NVDIMM performance went up in the remote test scenario. Doesn't surprise me at all. The big reason is that the CPU is doing half the work. It's not moving the data. The adapter is moving the data, right? So you have more CPU. Usually IOPS rise when that happens. Is that way off base, or did you have other evidence that surprised you?
Well, it's just not what I normally expect, but certainly we did consider that might have been the answer. With the remote, some of the work is getting split across CPUs from 2 different servers. So exactly as you said, it could be that when you do that.
In particular, no data movement on the initiator, right? The adapter is dropping the data at the destination address.
Right. Now, because we were using NVMe-oF fabrics, even for the persistent memory, the initiator CPU probably has to do some work, but
yeah.
all the data movement is offloaded.
It's not moving the data. It's
Correct.
just pushing RDMA buttons and saying, please move the data.
So we actually have CPU usage data that we didn't look at. So that could be
You
a
should,
follow-up.
but I think that'll explain the IOP bump.
Thank you, Tom.
Good, one more question of substance. Like the last one was. Yeah. Oh, they're waiting.
Marty?
Oh,
Question
once
here.
again in the front row, Marty.
So, besides the remote being faster than the local, there's another puzzle in your data, which is that, even when the IOPS are roughly the same, the latency might differ quite a bit for the same test, right? And that is sort of seems to contradict Little's law, which says that the two are related if the queue depth is the same, right? So any guesses as to why?
So for the real-world replay test, they're changing every step. It's not a fixed, constant workload. So I like to use the term blocking and tackling. So sometimes you get big block sizes in front of you. You can't get around it, right? You're backed up. Sometimes you get tackled. You're on your way and you get coalesced into something bigger. So
Yeah.
there's a
So the
lot
queue
of
depth
reasons
is
why.
changing
Right.
based on the target.
So the one thing we know for certain is we don't know for certain.
Okay.
Or as Eden said earlier, it depends.
All right. Thank you.
But generally speaking, yes, we saw that lower latency leads to higher IOPS. And except that Tom pointed out, there could be cases where you're splitting the work across, remote splits the work across more CPU cores.
Again, response times would be probably more important than the IOPS. I would pick a better consistent response time than a spike in IOPS, because generally you don't need the IO rate as much as you need consistency.
Very good. All right, give the presenters a hand, please.